Okay, we're going to have lab 2, and what I want to do is just go over some of the questions and some of the formula. I mean, you'll want to have the lab with you when you look at this. So here are two formulas, and here's another formula. This has no air resistance, and you might have seen these before. It's a body that's falling through the air. This is the velocity, and this is the height, and v naught is the initial velocity, and h naught is the initial height. And this is a model with air resistance. And so in other words, this is air resistance is what causes that to float. And notice that that falls differently than that. This equation says that's not the case. This says that everything falls the same way. This equation says that different objects with different mass and air resistance capability fall at different rates. And so Ogmund is going to talk a little bit about this. So I'm going to just do an example with these two. This is velocity and the time. This is velocity is in feet per second. And here the height is going to be in feet. And here the velocity is going to be in feet per second. Okay, so anyway, just do an example here. I have my initial velocity is 0. My initial height is 1,000. And I want to ask, how long does it take to fall 900 feet? Now, when you fall 900 feet, when you started, well, let's set this up. Hs of t is minus 16t squared. Initial velocity is 0, so we don't have to worry about that, plus 1,000. So if I fall 900 feet, my height is now 1,000. So if I fall 900 feet, my height is 100. So I have to solve this. And that's going to be this 16t squared equals 900. T squared equals 900 over 16. And that's going to be 7.5. That's what t is when you solve it. Okay, so how long does it take to fall 900 feet using this model? 7.5 seconds. Find Vs of t. So I take Vs of 7.5. I use this formula, minus 32 at 7.5 plus V naught. V naught is 0, so it's minus 32, 7.5 feet per second, and this is going to be equal to minus 240 feet per second. So that's what it's falling at. So that object starting at 1,000 feet, falling to 100 feet, takes 7.5 seconds to do that if there's no air resistance, and the speed at that point is minus 240 feet per second. Okay, so now I'm going to look at the same situation with this. This is question number 3. Compare to VRT. So what I want to do, so I want to find this VRT. So sorry, it's going to be VRTO. So I go, okay, VR 7.5, and that's going to equal m times g over k, 1 minus e to the minus k t over m. Okay. Now, again, these are just practice problems to get you sort of introduced to the concepts there. So I need to figure out what all this stuff is. Well, here m is 100, g is 32 feet, minus 32 feet per second. K is given, that's 2.5. In the problem, these are going to be different. So 1 minus e to the minus 2.5 times t is going to be this value, 7.5, and divided by the mass, m, which is 100. So I put this in, I crank this out, and I look at my calculating sheet where I did all this work, and what I get here is that this is 200 minus 218 feet per second. So air resistance has slowed this down compared to this model. And if the more we fell, the more you'd see the effective air resistance. So anyway, these are just a couple of problems to get you warmed up for the lab. I wanted to introduce you to the velocity, to the height function, which you'll need, also to this new velocity model with air resistance. I wanted to introduce you to what all these letters mean. Again, they're going to be different in your lab, and they have some questions to answer. And the upshot here is that the air resistance model tells us that we're falling a little bit slower than with the non-air resistance model. Now, of course, The bigger k is, the more this will vary and slow down. Okay. So anyway, have fun with that problem. It's based on a real-life problem of a free fall. Okay. So the second series of problems, number 4 and 5, have to do with what's called a multiplier, and it's an economic object, and this has a relationship to infinite series. And so here's the notion. I'm going to spend $1,000 at a store in Des Moines. I'm sorry, $100. And that store owner spends 80% of that somewhere else, at a restaurant, say. The workers at the restaurant spend 80% of that at a bookstore. And the bookstore people spend another 80% of that at a coffee shop. So I'm going to write an equation to describe this spending. And again, you're going to have this multiplier effect. You know, when you read the lab, you'll understand what I'm doing here. So here's the money spent. Okay, I spend 100. Okay. Now the store owner, he spends 80% of that. Okay. At a restaurant. And the waiters, they spend 80% of this at a bookstore. Now the bookstore people spend 80% of this so it's at a coffee shop, and so on. So we're going to say this finishes. Now, so I'm going to find out how much the money spent. That's going to be 100 plus 0.8 times 100 plus 0.88 times 100 plus 0.8 times 100 and this is going to be equal to 100 plus 0.8 times 100 plus 0.8 squared times 100 plus 0.8 cubed times 100 and so forth. Okay, so what I'm trying to do here is, again, the problem has to do with what's called an economic multiplier, and it's the notion that if you spend money somewhere in town, that person spends money at a certain rate. Wherever that person spends the money, those people in turn spend 80% that money at the same rate, and so forth. And so what you get when you do this is you get a series. And so I'm just trying to give you some insight when you do number 4 and 5, why there's an infinite series that turns up. And there's also a couple of homework problems that the problem talks about. So again, just to go over it briefly, I spent 100 at a store. That store owner spends 80% of that somewhere else at a restaurant. Those waiters spend 80% of what the store owner spent somewhere else, and so forth. And I write that up as an infinite, and I get a nice geometric series. Okay, so that's number 4 and 5. And then the last one has to do with this series here. And this series has a nice formula, which it's your job to figure it out. You can figure that out in lots of different ways. Again, read the problem. But what I want to do is I wanted to show you what you do. What you're going to do is plug in various values of m. So here's what I'm going to do. I'm going to plug in m equals 6 here. And that's just, to give you an idea, that's what the series is. So if I wanted to find S100, it would be this. The partial sum. And I used Wolfram alpha. And what I got for an answer was 0.239999. So 0.239 repeating. And that's about, so that's what I got for S100. Now your job is to use this to kind of guess at what this equals. Because what there is there's a nice formula. This is going to have a nice formula for it. And I'm not going to tell you what it is because I want you to think about it. But for here, I just want to point out that this is about 0.24. That's about 24. That's a 24 over 100 exactly. And if I reduce that, I divide this by 4, I get 6 over 25. Notice Notice this is also related to 6 in some fashion. So that's not an accident. So what you need to do is figure out the formula based on a bunch of exercises that you'll do in the problem. So real quickly, problem number 1 to 3, you've got to use these formulas. And here's some examples of how to use them. Problems 4 and 5, it's an economic multiplier, and here's an example of how it comes up. And number 6, it's an infinite series, and you need to figure out the formula. I hope this is helpful.